Hi everyone, my name is Fred Sigernes, and I'm going to do a lecture about how do we take color pictures of the aurora. Well, first of all, I'm sorry that we have to meet this way due to this pandemic situation. I'm sitting here in my wife's walk-in closet, and I cannot meet you. So this lecture had to be digital. And I also recommend you to use a computer screen for these lectures, because this recording is in full HD. That means 1920 by 1080 pixels. Okay, let's start the lecture. I'll share out my screen. That one, and share it. And now you should see it. So the topic today is how to take color pictures of the aurora. Now, I'm a professor at the University Center, or UNIS, and I'm also the chief scientist of the Kjell Henriksen Observatory, KHO, which is at Breinosa, about 12 kilometers from Longyearbyen. Let me now continue. Here we go. What is the dinner menu, so to say? Well, first of all, I will try to tell what is the motivation for this lecture. Then I will go into you need to know where the aurora is. So I will talk. I will point you into the direction where you can find the information about that. Then I will go into the regular digital single reflex camera. How do you set it up to take pictures of the aurora? Then I will continue with some scientific cameras, and what can we do with these color cameras? Okay, optics is maybe the oldest branch of modern physics. Started back with Newton, and when he started to play with the prism. But still, the development in optics is like a express train still running. So a lot has happened the last years, especially the last 2 decades. Now, these cameras, you can buy them in a shop. They are low cost and mass products. They have a high spatial resolution, and you get very sharp images with detail. And the sensitivity of these cameras are what we call are getting very good. We are talking ISO levels 25,000 and so on. It's a simple design, and the target that we're going to image, it seems like these color channels can detect the main auroral emissions. I'll come back to that. And what can we do with this color? And that is relatively new. We can run color classification. We can separate based on color what type of target we are looking at. They can operate almost in any light conditions, even with full moon. And it's relatively easy to calibrate them using stars, and you can find how the lens performs. And they are, of course, useful in public presentations. And but the cameras are not intensity calibrated. You don't know how much light is actually hitting your detector. Where is the aurora? Where is the target? Well, luckily, we have an app developed at the KHO, which is called Aurora Forecast 3D. And that is a tool to track down where the aurora is located in the sky from any location on the planet. And I highly recommend you, actually you should go in and watch the YouTube video where I demonstrate the app. So I leave it up to you to have a look at this demonstration of the app. And you can download the app, it's of course free. So that's all I'm going to say about where the aurora is in this lecture. And I will concentrate on the camera. Okay, how does a camera work? So here is a sketch of the digital single lens reflex camera. So you have a lens objective here for a lens. You have a mirror, 45-degree, which flips up when you take the image. And you have a detector behind here in the image plane. Simplified, this can be viewed like this. You have your target object here, the Aurora, and light that goes from this point through the center of the lens will go straight through the lens. Light that comes parallel towards the lens will focus through the focal point of the lens up here, and light that goes through the focal point at the front will go parallel out like this. And you will have an image. And in this image, we'll put a CCD, or a charge coupled device, electronic film, so to say. And that will record your image. In addition, we have an aperture stop. That is usually this inner ring here. And since the Aurora is a weak target, it's not much light, you have to open this aperture all the way. And you do that by turning this inner ring to a low number, a low F value number. So this is the quick menu. So you should first look where you expect the Aurora to occur by using the Aurora forecast. Also check the local weather conditions. You should also use a tripod and a self-trigger to take images, because the Aurora is moving fast, and you will use second exposures, maybe 2, 3, 5 second long exposures. You should remember to open the aperture to maximum or low F value number. And also important, set the focus to infinity before you start. Remember, it's cold and it's dark when you're out there. So to save time, trim the lens to infinity. But what should you use, ISO settings should you use on the detector? And that's a more tricky question that I will try to answer. First, a little bit about the CCD, or the charge coupled device. What is it? Well, it is using the photoelectric effect. So when a little photon hits a metal surface or a solids like phosphorus doped silicon, then it will kick loose an electron. And these are these small surfaces I'm talking about, this grayed out, and you have a whole bunch of them stacked together in a frame. On top here you have colored glass, for example, blue and 2 green ones and 1 red. This is called the color filter mosaic. And that's there so that you can make color images. So how is the working principle here? Well, this is a simplified version. Let's think you have a bunch of buckets and it's raining. So how does it work, this CCD? Well, at some point in time, if you start counting raindrops, you transfer this conveyor belt here over to a readout conveyor belt, which actually reads how much water drops did you get in each of the buckets, and then you measure it. And the more rain you have, the more intense is the intensity of your image. So you should think of the water drops as small photons or light photons hitting your metal surfaces. So that's a working principle of a CCD, and this is the readout conveyor belt, or the readout shift register. So here's an image from Olympus showing you this architecture with electronics. So this is the serial CCD shift register, which corresponds to this conveyor belt here. Okay. What about the target? That's important. If you look at a Aurora arc here, it stretches from around 100 kilometers of altitude all the way up to 600-700 kilometers of altitude. And notice that on top of the arc, the arc is red. This you don't usually see with your eyes because your eye is not that sensitive to red. But you see the green, and that's lower down in the atmospheric column. So what's happening? Well, these electrons that comes from the solar wind or from the sun, they are guided by the magnetic field. And when they hit the upper atmospheric atoms, oxygen atoms, like this, well, an oxygen atom is an atom where you have 8 electrons spinning around its core. After the collision, one of these electrons will be in a higher orbit. And when it falls down, it will emit a specific quanta of light at a specific wavelength. So if the energy is relatively low, you will have red. And this emission has a lifetime of 110 seconds. So it actually is a very diffuse target we are looking at on top of the arc. If the energy is a little bit higher, then you will have green, and the electrons goes further down and collides further down into the atmosphere. And the lifetime of that emission is 1 second. So you will see more structured emissions in green, which you actually see with your eye. Note that this exposure was overexposed, so much of the structure is washed out. Here is a 30-second exposure at ISO 1600, and the aperture is set to 2.8. This was one of the first cameras we played with. So if the energy is even higher, it will start, the electrons will hit a wall down here at about 100 kilometers of altitude, and that's where the electrons collide with molecules, which are more heavier than atoms, and you can see them as fast-moving blobs in the lower part of the aurora curtain. So the light emitted here is emitted at a specific wavelength. It's an emission line. So the green line emits at wavelength 557.7 nanometer, or 5,577 angstrom, and the red one comes from the 6,300 angstrom wavelength, also from oxygen. So how does this fit into your camera? Well, okay, here's the spectrum of the aurora throughout the visible part of the electromagnetic spectrum, from 400, 4,000 to 7,000 angstrom. And this is the intensity in Rayleigh per angstrom. And 1 Rayleigh is 1 million photons per square centimeter per second. And here you see the spectrum. The blue curve is the day-side typical spectrum, aurora, and the red curve is night-side aurora over here. And notice how strong the green line is, and here you have the red line of the aurora. These are the dominating lines from oxygen. We also have some molecular lines higher up here in the red, and some here, and also in the blue. But they are very weak compared to the red and the green line emissions of the aurora. The dotted line behind here is actually the spectral response of a digital single reflex camera. And notice that the peaks do not match. But still we see that we can easily detect the green line, and we can also detect the red line. So the 2 main auroral emissions in the aurora, auroral emissions, they are detectable by DSLR cameras. One other important feature is the unity gain ISO of your camera. And what is that? The unity gain ISO of the camera is where the analog digital converter digitizes 1 electron to one data number. And that is the smallest quantum that makes sense to digitize. You can't digitize less than one electron. Remember, it takes a lot of photons to generate one electron. So here's a typical curve for different cameras showing the pixel size and the unit ISO gain. And if you have a Nikon D300, which has about 5.5 micrometer pixels, you have a unit ISO of around 1100. So put your camera to ISO value 1100, and then you have the most sensitive settings for your camera. So please, this homepage here explains it very well, and you can go and check what your unity gain ISO is for your camera. Now, I would like to focus a little bit on scientific cameras. We have different types. We have the EMCCD and we have the ICCD. That's a electron multiplying charge coupled device. That's the EMCCD, and the ICCD is a intensified CCD. Let's have a look, more close look. Here's the EMCCD camera. Well, it looks more or less like a CCD camera, but you actually put the extra amplifier on the readout circuit or the read glass in your circuit, and using high voltage. And that makes these sensors about 100 times more sensitive than the regular CCD. So these photoelectrons coming out of the CCD is amplified by impact ionization through a high voltage serial register. The ICCD camera, well, here you see a typical one. You have a front lens here, a filter wheel, and some relay optics. And then you have an intensifier here and just a regular video camera looking at the intensifier. What's going on? Well, what you have is a photocathode where the light comes in and it hits a metal plate, a microchannel plate, and you have high voltage applied here as well. And then this light hits a phosphor screen. Here is the drawing. Kicks loose more electrons, higher signal, and when those electrons hits the phosphor screen, you can view the output. This is the old way of doing it, and this is how they look. And here's a small EMCCD with a Bayer mosaic on top of the imaging plane. And that makes it a color EMCCD. And I will show you some data from that instrument. Here's an event from the 4th of December 2013, where I have synchronized data from different types of cameras that I want to show you. This event was not detected by satellites up in the solar wind, and so it was not forecasted. So it's believed to be associated with some sort of cool rotating interactive region in the solar wind, and it kicked in here at the 13th of December at about 7 o'clock. If you want to know more about how magnetic activity and aurora is connected, please go to this YouTube video here, down here, and have a look at that one. So here's the sequence. This is a DSLR camera. Here's an intensified version, and here's the EMCCD color camera. Notice the exposure time here is 5 seconds. Here we have 25 images per second with the intensified CCD, and so it's the most sensitive camera here. But note it's not color. The EMCCD has about 1 exposure per second. But look at the beautiful detail you get with these high-speed cameras compared to a regular DSLR camera. And also notice the price. Well, that's interesting. You can get a DSLR camera for around $1,000, more advanced mirrorless one for maybe $2,000. This is a price jump up to the intensified cameras at $60,000, and even more if you put filter wheels and so on into them. But here, look at this. The color EM-CCD is around $9,000, so that's pretty good. And what can we do with it? Look here. If you take the color image and we use a hue, saturation, lightness color table and pick out a cake slice like this and only represent those colors, you can see that we can actually find whether we have Aurora or not using a computer, which is interesting if we want to do it automatic. Furthermore, we do the same with the EM-CCD. The result is more or less the same, but a little bit more noisy. And you see there are some misclassifications here. So more development is needed to make this method more robust. Furthermore, here's a new type of cameras that has arrived, the CMOS cameras. They are basically the same as the CCD, but under each pixel, there is a measuring glass. So there is no conveyor belt applied. But notice here how you can see stars, you can see the aurora, you can even see satellites flying by here. Watch here. So this is the new generation of cameras, and the price is comparable to a regular DSLR camera. Oh, there's a new satellite. Watch it. Oops. And this is only 1 second exposure. And what else can we do? Well, if we take one line column of the image detector from, for example, from north to south, and stack it in time, we get what we call a kilogram. So here you see, from north to south, we see a lot of aurora crossing that column in the image sensor. So from north to south. So here we have a lot of aurora. Here we have daylight. The sun is coming up. Sky is blue, and more aurora. The oval seems to be moving southward in this case. So this was a clear day with lots of aurora, and so on. Here is another clear day with lots of aurora, but in this case we had a lot of ice in the stratosphere between the mainland and Svalbard. So we got scattered light into the winter. A red scattered light. So this is known as the red sky enigma. And the last example here is a cloudy day. You see no structure, a lot of light pollution from Mine 7 and the dog villages. So what is it to remember from this lecture? Well, it's important to check out the local weather forecast and the aurora forecast to see if you have a chance to see aurora. Also, use a tripod and a self-trigger. Use maximum aperture. Open up the lens all the way, lowest f value. Set the focus to infinity before you start imaging. Find your camera unity gain ISO for your camera. And also you should know about the different types of detectors that are available. We have the CCD, charge-coupled device. You have the CMOS, which is more or less the same thing as the CCD, except that you use a different readout circuit. You have the ICCD, the intensified CCD, which is using an image intensifier. And you have the EM-CCD, which is using high voltage to read out the signal of the CCD. And also, as new technology arrives in imaging technology, we expect to further develop new technique for color segmentation and classification. Okay, I think that's it. Thank you for watching this lecture, and have a good time.